I am Alex.
I'm Kenny, and this is our project for very small scale localization through IR. So there's an increasing number of IoT and wearable devices that are entering the market, and they could potentially benefit from knowing their locations with respect to one another on the person's body. And so we want to come up with a localization scheme that reaches down to zero point 0.5 meters of accuracy and can function without the use of stationary beacons that could hinder the operation of whatever device integrates this. So our approach is to use IR to track the relative distance between custom-made nodes that can be integrated into real-world systems to track the distance between these devices. Each of our custom-made nodes will include an Arduino Nano 33BLE sense, an emitter IR circuit, and a couple IR receiver circuits. Our nodes will communicate with each other through BLE to coordinate which ones will be emitting IR, which ones will be receiving IR. And we'll also set up this network in a way that's flexible enough to work with any number of nodes. With the measured IR data, along with the integrated IMU's data, we will pass that through a neural network and generate a very accurate estimation of the distance between nodes. And all of that will be passed over to every node in the network, so they'll be able to estimate the distance from one another and get an idea of where every device is. So here's a really quick example of how this would function with three nodes. In the first picture, we can see node 1 emitting IR to the surrounding area, and node 2 and node 3 measuring different strengths of IR. This process repeats for node 2, which will emit its own IR, and for nodes 1 and 3 to receive, and this will repeat for node 3. This is an overview of what each node looks like at a circuit level. So each of those receiver circuits that are labeled on the diagram to the left will be measuring the IR magnitude received from a different node's emitter. That data will be used to calculate the distance between two nodes, and using multiple receiver allows us to estimate the angle between the nodes as shown in the diagram at the right. So since all of our distance measurements rely very heavily on the magnitude of IR received, we want to make sure that our dispersion is very even and symmetric. So this diagram shows our plan to do so. We want to have one emitter node dispersing IR upwards, and then having a reflector at the top bouncing that IR back downwards in a larger, more circular symmetric pattern for any other IR receiver nodes in the area to receive. So with our technical plans laid out, we first started by working on the hardware and physical design of our system. First, we made our own PCB board to hold the Arduino with all of its IR emitter and receiver circuits. Along with that, we made our own 3D printed frame so that it would be able to hold the PCB with the reflectors in a very symmetric design so that all of our nodes would be symmetric and consistent across the board. For our reflectors, we chose to use cardboard covered with aluminum foil since those are very easy to make and very cost efficient. As we got further into our design process, we realized that we had an issue with our circuit design, primarily because of the high current draw, which can cause brownouts and cause our system to crash. This comes from the BLE radios, the IR emitters, and the IR receivers, which all draw a lot of current, and that exceeds the Arduino's power supply limit. Additionally, we realized that by using a USB splitter, we're splitting the USB protocol's current limit between two Arduinos, and that would once again cause at least one of them to brown out and crash. We also ran into some issues when developing our BLE network, which has changed dramatically from the network that we had for our midterm presentation. We realized that although the Arduino BLE library suggests that they can handle more than two devices, their developers are still working on adding in the features to support more. So we had to come up with a new connectionless network that meets our design specs, that can support more than two devices and still transfer data. We came up with a new connectionless network that transfers data by storing it inside of the device's local name and broadcasting whenever they want to transmit data or scanning whenever they want to receive data. The broadcasted service UUID is used as a key to verify whether a device is in fact an IR node or just some other random BLE device. This network still meets our design goals, but with an additional amount of latency and instability issues that we can go into further later. But for now, here's an example of our network working with three nodes as an example. So in the first stage, all of the nodes will be broadcasting their unique IDs, and that allows them to all understand the size of the network and the number of nodes connected. They all come with their own unique IDs, which will set the order in which they can scan or broadcast in. So as you can see in stage 2, 3, and 4, only one node at a time is scanning or listening for new data to receive, and 2 nodes are broadcasting their data outwards for that node to receive. So in stage 2, you can see that only node number 1 is allowed to listen. Stage 3 has only node number 2 that is listening, and stage 4 only has node number 3 that is listening, while all the others are broadcasting. So as mentioned earlier, this is an unconventional connectionless network, and so this contributes a lot of latency to all of our data exchanges. In addition to that, it takes a lot of power to broadcast and scan for new data. This consumes a lot of power and contributes to the power supply issues that we mentioned earlier. We'll go into our solutions to these problems further on later.
Here's the state machine we designed to use with the connectionless network Kenny just described. So after the discovery phase, where each node discovers the IDs of all other nodes and orders them in ascending order to agree upon the order in which they will take turns to be the emitter. The node with the lowest ID starts in state 0. The other nodes all start in state 2. So just tracing the path of one node through the circuit, through the state machine, starting in node 0, after emitting IR, or starting in state 0, emitting IR, the node will wait until all the other states have taken their readings. Then it will move to state 1 and listen for the transmitted readings. After it receives those readings over Bluetooth, it moves to state 2 and waits for the next emitter or next beacon to start emitting IR. After that, it moves to state 3, takes its measurements, then moves to state 4 and transmits its measurements to the other nodes. And after that, it waits for the emitter to relinquish control, and then moves to state 5, where it decides whether or not it is going back to be a receiving node or an emitting node in the next cycle. We store measurements and IDs for each node in a 2D array. So this is first initialized during the discovery period, where each node's ID is placed in the first column of this 2D array. And after all IDs are discovered, we sort numerically. After that, as you move through the state machine, the rest of the columns are filled out, and the state column is updated every cycle, or every time an updated state is received by the nodes. In order to get a valid reading for an IR receiver, we need to take a measurement while the emitter on the emitting node is high. So to do this, we had an original test diagram as shown below, where we took 12 readings 1 millisecond apart to ensure that at least one measurement was fully in one of the high cycles. In our current version, using the state machine, we do something very similar, but instead of the time period here that we need to cover being 10 milliseconds, we take readings for the total loop time during which the node is broadcasting or receiving state value, as well as the pulse time, to achieve the same effect, but the downtime is somewhat longer in the middle. One of the biggest issues with this project that we mentioned during our midterm presentation was that the columns in our design substantially interfere with the radiation pattern for the IR LEDs. In order to solve this, we decided to use a neural network and collect data at each angle, or at a variety of angles and distances around the central beacon. So the diagram on the right here shows the gray dots, various locations where we would take readings, and in each of these locations, whatever the remote node is, would have one of 12 orientations shown by the arrows below. Unfortunately, due to the high latency of the BLE communication network we ended up designing, and the unfortunate problems with the Arduino crashing due to our power supply issues, we were not able to collect data very quickly. So we were only able to collect a small subset of this ideal set of data. Fortunately, those results were very promising. We used a neural network with inner layers of 30, 18, and 12 respectively to calculate distance and angle based on the data we collected. Unfortunately, as you can see here, the measurements for angle were not nearly as good as distance. So while we got very good, very promising results for distance, the angle, I think, needs the full set of data to be collected before that would increase the accuracy. This shows that the neural network method is very promising for distances, and likely with more data would be very promising for angle estimation as well.
We also wanted a way to visualize our results, so we wrote a script to read the outputs of an Arduino and plot the location of every node on a single coordinate system. The idea is that a single Arduino will print its data outputs to a computer running this script. This data will contain the location of every node relative to its position. And so you can see from the example on the bottom, with the picture on the left, we have one node printing out the location of two others. And later on, once we move one of those nodes further away, we see that the visualizer accordingly moves that node further away from the center. Unfortunately, we weren't actually able to get the script to work with our nodes because of our latency issues and our stability from power issues.
I will use two nodes for this demonstration. This node will be node 1, this node will be node 2. Node 1 uses COM4, node 2 uses COM7. So I have opened the serial ports here. Right now, they're waiting to calibrate the compass. So I will rotate them 360 degrees to get good compass reading. And then I'll press continue. After I press continue for each of the modules, they move to the state of looking for other nodes and trying to identify their IDs. So as you can see, node 1 has first listed its ID of 274 and has found the second node 283. The other node has also found the same, so I will tell both of them to continue. Alright, so both have sorted the nodes and agreed on an order. So now I just need to take measurements. These measurements look better without light, so I will turn off my desk lamp here. Or first I will position them. Alright. Now I'll hit continue. So the latency is not good, as we go over in our report, for several reasons. But as you can see, the first set of data was printed out by module 1, and then module 2 is printed. So the order from left to right of print out here is the local compass reading, the local IR readings for the next 3 values, and then the remote compass reading and the remote IR values for the next 3 readings after that. So as you can see here, one of the IR readings is noticeably higher than the others in each case. And as I move beacons, which I'm doing off the screen right now, the values change slightly and which beacon is reading the highest changes.
So for future directions, we want to resolve the power supply issues that we talked about earlier. We can do this by switching to batteries and using a new voltage regulator that handles higher current. We also want to switch to a wireless communication protocol that actually supports more than 2 devices, such as Wi-Fi. Once we have that set up, we also want to switch our visualizer so that it actually joins the network as a device in the network. That way, our nodes are not tied down by having to be connected to a computer through a serial port. We also want to improve our neural network by collecting more data so that we can train the network further, improve our accuracy. And we also want to adjust the node frame design such that we don't have pillars holding up the reflectors as we currently do. We can do this by switching to a new type of plastic that is transparent to IR light.